Sole smato a mai lo touched up. Quante senen. Sole smato a mai lo touched up. Quante senen. She was shining, thought of her skin and the Friday.
Yo, it's me again today. I've already done, so I did a lot today, and so I'm not gonna do too much now. I want to finish this chapter and write everything for this chapter if I can. Might take a while though, because I'm gonna be reading it and breaking it down. Before moving on to the next chapter, because the next chapter involves actually doing some projects, which I've done before, mind you. It's not the same, I haven't done the same projects before, but I think the structure in this book is a lot better than what I did in university, which is nice. Because I looked at it briefly earlier, which is cool. So I'll be doing that. Alright, so I'm going to be reading a little bit, but I won't. I'll probably just keep it silent unless somebody wants to actually listen. But other than that, I'm just gonna keep going. I am currently in. So I'm in. So I am currently. I got a haircut today, by the way, if anyone cares. Very short. So I am currently looking at. I'm looking at instance-based learning, and then we're moving on from instance-based to model-based learning. And then once that is complete, I believe the next part is talking about the main challenges of machine learning, and then we have non-representative data, training data. This can be outliers, things like that. And then we talk about bias here, which is cool. Poor quality data. This is generally outliers, noise, errors. But I want to go through everything, and then overfitting. It'll talk more in depth with overfitting, which is overgeneralizing basically. If you have data that is, so like it's just overgeneralizing the data, and when you overgeneralize something, it can be incorrect because it's overgeneralizing for one data point or one instance, which can be really bad. And this can be due to the fact that the model might be a bit too complex for the data, in which case you need to, I believe here this mentioned actually, happens when the model is too complex relative to the amount of noisiness for the training data. The possible solutions are to simplify the model by selecting one with fewer parameters, e.g. linear model rather than a high degree polynomial model. So this can be done by, for example, if you're using a polynomial one like this one here, a polynomial regression, then you can apply a linear regression and hope to get like a better result. Like as you can see here, you can see how these dots are going like this. This might not be that good, so maybe making it linear, so you can imagine like a line going across here, it predicts a little bit better rather than like being heavily weighted on a single data point like this one here, where it's going sharp down. That the bias is too strong, or the model is too complex to encapsulate all of the information, which is cool. So you can gather more training data to account for this as well. I think, for example, if you were to, get more training data that was generalized for these later ends here, this wouldn't be occurring. It would be a more squiggly like this one here, but in general, you can fix the data itself, so you can remove these stragglers at the end. If you do remove this whole section here, then this graph would look a lot different because it wouldn't have this information here. So yeah, we talk about this later. So we will go over this, and I believe the book goes over it. So we're gonna go. This might actually take longer than I thought. We might not actually hit this part because there is a lot. And then there's little exercises. These are just questions. So this should help me make sure that I am understanding every concept. And if I'm hesitating on any of them, I will go back, reread the section, make sure I understand it, and then move on. And then eventually, hopefully with every question, after that's answered or after that is done, then we move on to chapter 2, which is end-to-end machine learning project. So this is generally following a step. This is the step-by-step. look at the big picture, get the data that we want, we discover and visualize the data to gain insights about the data, so we can determine what we can apply to the data. You know, we might want to prepare it by cleaning the information, and then we select the model and then train it, fine-tune it based on some of the results of the validation that we have to validate the model as well, and then we test it, present the solution, and finish it off. There's a bunch of data sets that we can look into, but I don't know if we'll be following exactly what they're doing, but for the most part, I'm just simply going to read, and maybe I'll do like a project maybe at the end. But this one looks like it's a lot more in-depth with calculations, some code, which is ideal. I like that. So here I think here you go. He's made a little project that we can do. So download the data, so you can do that. We can follow the whole example as well, which is cool. We can use Jupyter, but we can make things easier and just use Google Drive. Google Jupyter. So it's like pretty good. And then we can do that. We can follow that project. So this is way down the line. This is in chapter 2, so I don't think we're going to reach here. I'm just going to continue to read from instance-based learning. And then explain to me right now, sir. I can't stop and explain. I'm just going to continue and move on. Like, I'm going to continue and keep going, basically. I'm currently on instance-based. I can't go all the way back and explain everything. So I'm up to instance-based learning. I'm going to read this part and then I'm going to write about it a little bit. That's how I'm going to do it. I'm going to read it, make sure I get it by writing it in my own words, and then going from there. Give me a rundown of the previous session. It was literally, we were learning about batch and online learning. And we were finishing up semi-supervised and reinforcement learning. I think that's where we left off. I want to say that's where we left off. In 3 sentences. Okay. Well, okay, I'll try. I'll do a brief. So semi-supervised is information. It's a semi-supervised learning is a learning form where the machine or the system takes in data that is partially labeled, mostly unlabeled. An example of semi-supervised learning is Google Photos, where it's primarily trained unsupervised, meaning that it runs clustering algorithms on images, for example, to gain like the most common occurrences of an image, right? Like in the image rather. So you have a group of pixels, right? For example, like Tony's face. Tony's face is going to generally have the same types of formation of pixels on that image, and so the computer doesn't know what that is, so the user actually will label that as Tony, and every instance of Tony in your album will occur as Tony, and those groups of that is like semi-supervised learning, where it's clustering algorithm initially, and then it's labeled after by the user itself. Okay, give me a second. I'll be right back. I gotta grab my food. Yo, I'm back. So I'm back. So the next part of after we did semi-supervised learning, we did something called, well, we looked at something called, it's a very different type of learning. It's called reinforcement learning, and it's probably one of the most, I guess, common ones that people kind of associate machine learning with, because it's less pre-trained data, it's less involving pre-trained data or pre-processed data by the developer, and it's more about, so reinforcement learning, so I'll just explain what it is. Reinforcement learning, in this case, the machine system is actually an agent that employs a series of policies. These policies can be considered like strategies, and based on the type of policy and what it achieves on the task. So for example, if an agent in this case could be considered a robot, the robot is given a series of actions in the form of functions. You can assume that, right? So the robot has the capability of observing its surroundings. It has the capability of moving a series of limbs, etc., etc. And based on the type of policy, aka the strategy it uses, you can reward it or penalize it based on the type of movement. Now, this is obviously, it's generally there'll be a task like, hey, robot, I want you to walk, right? And based on how the robot tends to move, you can reward it or penalize it, and it will do something less if you penalize it more often on the thing that you don't want it to do, and if you reward it often, then it will continue to do that movement or refine that movement, or etc., etc. So it's a very different type where the data is like streaming and constantly being fed to itself, trying to understand. So an example is like, if you know the AlphaGo. AlphaGo is the the Go robot that beat the world championship. So initially this robot, or this particular system, it analyzed millions of games first, and then it would train against itself to get better, and it would get rewards based on correct moves or the quality of moves, etc., etc. And then that's how it's like reinforcement. So you keep brute forcing your way until you get the perfect result, basically. That's what reinforcement learning is. It's kind of like explained in the name as well. So that's that, and then we moved on to batch learning. So batch learning is, it's these are basically ways to classify. So what I'm going through right now is basically ways to classify machine learning systems. So there's systems that may want to batch learn. Batch learning is generally done when you can afford to have a long period of time between particular model versions. So for example, let's say you have a machine learning system version 1, and this version of this system is responsible for filtering out unwanted emails that are spam emails or something like that, right? And now let's say over time, let's say over a week's time, these spammers have found a way to kind of circumvent the system, and you have finally noticed, or you have noticed. And so what you do is you would take those new instances or those new situations where those spammers have tried to circumvent, and you add them to your data set, and then you retrain a new model or a new version of that machine learning system, and then you deploy it and replace the previous version, and now it should account for the new tricks that those spammers are trying to employ to circumvent the system. Now you've accounted for them. And batch learning is simple. It works well in some cases. If you can afford to have the gap between versions, then you're fine. In my previous company, for example, we ran a object detection system, and this object detection system didn't necessarily require a constant stream of data learning. It didn't need to learn constantly. So we would have new versions maybe every few months, depending on the type of the change in data. Maybe the client was complaining that the lighting was too strong, and we need to account for this, and so we have a bunch of new data that's added to the dataset and retrain the model, and then upload the new version of that model. That's called batch training. It's simple, but it's not suitable for rapid situations like a stock market, for example, where you need to respond rapidly based on streaming data. And in those cases, you would use online learning, which is an alternative that I'll get into soon. But batch learning is also really resource intensive. It can be automated, so it can be like without human intervention, but it's very resource intensive and quite expensive because you're training on the entire data set, and it's constantly getting bigger and bigger based on the new data that you get. And on top of that, it costs a lot of like CPU usage and like input output, all that stuff. Trying to like run through it in my head. Just this is based on my head right now. Yeah, so it's expensive as well. And it's generally done offline. It's not done online, meaning that it's not done on the live version of the model. So there won't be any performance dips. So that's like a benefit as well. The user is not going to observe performance dips if there are other users trying to abuse the system to try and manipulate the system's output. And so moving on to the alternative is online learning, and online learning is the alternative where there is a live model or live system running, for example, like a stock market bot, and as new data is appearing on the stock market, that stream of data is added, and it is constantly being learned by the system. So that's like a case of rapid learning, which is great. The benefit of this is like for systems that can't handle large amounts of data, like for batch learning, like something like the Mars rover or something like that, it can't hold like huge amounts of data. So it's beneficial for things like that, because what they would do is, as the new data comes in, you can disregard the previous data unless you want to roll back to a previous state of that model. So the new version will constantly being updated while discarding older versions or older data that is not required. So it's really good for like systems that don't have a lot of space or a lot of memory to do hefty training sessions. The challenges for the online learning though is that because it's so rapid, it's kind of volatile. So a user can kind of abuse this system by constantly spamming the same name. For example, a search engine, they can spam the same, maybe their own website, they can spam it 100 times in the search engine, and so that it can rank higher in the search engine. And so that's like a way you can abuse it. And in worst case scenarios, it can actually considerably decrease the performance of the system, and your clients will obviously notice. You can pair online learning with other methods, so you need to constantly monitor online learning if you're going to use it. And a way to kind of like prevent malicious kind of or abusing the system is by adding a anomaly detection method, where, as we mentioned earlier, I believe it's up in the unsupervised section. Yeah, here it is. So we have in the unsupervised learning, you're going to employ unsupervised learning, where the new data is actually gone through an anomaly detection algorithm, something like one class SVM, and then it can filter out those outlier responses that you are noticing that are occurring to try and abuse the system, and then you pass the data to the whatever the other model is. So you could do that. That's cool. And that's what online learning is generally for rapid situations. There's also another kind of combination, I would say, of learning that happens. Like it's another version where it's called out of core learning. And out of core learning is basically, imagine like a huge data set, and let's say your computer can't hold all of that, right? Let's say you have like a hard drive with a massive data set and you don't want to train it all in one go. What you can do is you can split this data up into, it's a form of online learning, but it is a bit confusing because this type out of core learning is actually done offline. Just think of it as incremental learning. So the big data is broken down into groups of small data, and this small data is then processed one by one until it's finished, and then you deploy the new system up, replacing the old one. So that's that. Excuse me. And then what else? Oh yeah. And then and that was like the last thing that we touched upon. Today I'm learning, or I read through this already, but I'm going through it again and taking notes. We're learning about instance-based learning and model-based learning. I'll see how far I get with that. So I'm gonna read through it after I finish my food, and then yeah. So give me like 5 minutes. I'll finish my food and then we'll start reading. Yes. Yes, I do. Yes, in fact, I do that. Okay. Thank you. I love Silva. Did you play Balatro yesterday? I forgot to check the VOD this time. Wait, I did play Balatro, man. Yeah, we did, remember? You look like such a nerd. Bro, I'm sick. I'm sick. Hello. Shalom. Hello. He really is the excuse me guy. Okay, I'll take these off, man. I don't need these, alright? I can live without them. Okay, buddy? He is him. I'm sick. Alright, I'm gonna continue, okay? I'm gonna continue reading. Okay. Okay. If you had that, look, if you had tats, you would look like a thug. Tattoos, nice. Would I? All right, what are we doing, man? Can we focus? All right, focus up, boys. All right. Possibly the most. Okay, so we're doing it. All right. Are we ready? Are we ready? This is instance-based learning, okay? Remember, the true goal of our model or our machine learning system is to basically evaluate new instances that have not been trained on before, right? We're not trying to, we might evaluate and generalize trained examples, you know, the stuff that we trained our system on really well. But if it doesn't, you know, respond well to new instances, then and it doesn't generalize new instances correctly, then there's, you know, there's a problem. So there's two ways we can do this. The approaches are the two main approaches to generalization is instance and model based. Okay, we're gonna start with the instance. So possibly the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to also flag emails that are very similar to known spam emails. So, this requires a measure of similarity between two emails. A very basic similarity measure between two emails could be to count the number of words they have in common. The system would flag an email as spam if it has many words in common with the known spam email. This is called instance-based learning. The system learns the examples by heart and then it generalizes to new cases by comparing them to the learned example or a subset of them using a similarity measure. For example, in figure 115, the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. So this is the new instance over here, and I assume that that's what that's trying to say. The X is the new instance, so there's two triangles that are closest to this. Therefore, we're going to classify it as an instance. We're going to classify it as a triangle. I assume that's what's going on. 20 push-ups. Dude, I'm not doing 20 push-ups. I'm not doing 20 push-ups, bro. So now we have model-based learning. Okay, so this is the other way, okay? Another way to generalize from a set of examples is to build a model of these examples. Then use that model to make predictions. This is called model-based learning. So, here we can see an example of model-based learning. So I'm trying to understand this. It's probably going to explain it anyway. So for example, suppose you want to know if money makes people happy. So you download the Better Life Index, the BLI, if I would say, from the OECD's website, as well as stats about GDP per capita, IMFs, or whatever. Then you join the tables and sort by GDP per capita. And table 1.1 shows that. shows an excerpt of what you get. So this is the example. So we have Hungary, GDP, capital USD, life satisfaction. So does people money make people happy? So let's plot the data for a few random countries. So here we go. We got Hungary, we got Korea, we got France, we got Australia, and we have the US. Okay. Do you see a trend here? Well, yeah. Generally, if I'm not stupid, it's going up. You know what I'm saying? It's going up slowly, slowly. There does seem to be a trend here, although the data is noisy, i.e. partly random. It looks like life satisfaction goes up more or less linearly as the country's GDP per capita increases. So you decide to model life satisfaction as a linear function of GDP per capita. This step is called model selection. You select a linear model of life satisfaction with just one attribute, GDP per capita. Cool. 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 Wait, bro, I was reading the next sentence. What? What happened? Keep it scrolling. Okay. Equation 1-1. A simple linear model. Life satisfaction is equal to theta 0 plus theta 1 multiplied by GDP per capita. Okay. This model has two model parameters. We have theta 0 and theta 1. By tweaking these parameters, you could make your model represent any linear function as shown in figure 118. We're about to put a linear regression model in about 3 pages. What? Listen, man, I'm just reading and I need to digest this, okay, as I go. Alright, theta 0, 8, theta 1, minus 5 times 10 to the negative 5. So that's the line that it produces. This is the line that this one produces, and this is the line that this one produces. A few possible linear models. Okay, before you can use your model, you need to define the parameter values of theta 0 and theta 1. How can you know which values will make your model perform best? To answer this question, you need to specify a performance measure. You can either define a utility function or fitness function that measures how good your model is, or you can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training examples. The objective is to minimize this distance. This is where the linear regression algorithm comes in. You feed it your training examples and it finds the parameters that make the linear model fit best to your data. This is called Was I mute for that entire interaction there? Was I? What did you guys hear in that entire conversation? I was muted? Okay, good. No, I heard everything. Damn it. Alright. Okay, so before you can, where was I? Minimize this distance. So the objective is to minimize the distance. That's the problem. That's the idea of behind the cost. So this is where linear regression algorithm comes in. You feed it your training examples and it finds the parameters that make the linear model fit best to your data. This is called training the model, right? In quotations. In our case, the algorithm finds that the optimal parameter values are theta 0 equal 4.85 and theta 1 is 4.91 multiplied 10 to the power of negative 5. This is the 10. The 10 thing is like the one, how many decimal things it goes back, right? 1, 2, 3. That's what that is, right? I'm not like high, if I remember. It goes back. if I remember. Yeah. That's the one. Yeah, I remember that. Sorry. So yeah, the linear model that fits the training data best. So this is shown here in this blue line here. We can see that. Cool. So here we can assume that 0 will be around here between probably like 5, and then 10,000 is around here, and then it keeps going up. Okay. This is odd though, because it's kind of weird, but whatever, it doesn't matter. Okay. You are finally ready to run the model to make predictions. For example, say you want to know how happy Cypriots are. Cyprus? Is that what Cypriots? I don't know. Are, and OECD data does not have the answer. Fortunately, you can use your model to make a good prediction. You look up Cyprus. Oh, it is Cyprus. Cyprus's GDP per capita. Find 22K, 22,587, and then apply your model and find that life satisfaction. That life satisfaction is likely to be somewhere around 4 equals 5.96. Somewhere around here. So where is it? 22. So if 22 is around here, it'll be around here. Yeah, makes sense. To fit, how do you say that? To fit your appetite, to whet your appetite. Don't know what it means. I see. Wait, I need to search this up because I'm a bit of a soy. How do I say it?
Wet.
To whet. Okay, got it. Thanks, bro. To whet your appetite. Shows the Python code that loads the data, prepares it. Wait, sorry. Let me just to whet your appetite. Example 1 shows the Python code that loads the data, prepares a scatter plot for visualization, and trains in a linear model, makes predictions on 7. Okay, cool. So here's the example code. So yep, I've seen this before. Oh, I've recognized this before. I've done this before in the data mining papers. So I've seen all of this before. Loading the data. You generally prepare the data. You can visualize the data here in a scatter plot, and then you run a linear model here, and then train the model, and then make a prediction. Bang, bada boom, bada pow. So here, so it says here the prepare function defines is not shown here. See this chapter in Jupyter Notebook if you want all gory details. It's just boring pandas code that joins the life satisfaction data from the OECD with GDP per day. So I know, yeah, that's fine. It's okay if you don't understand all code yet, but okay, cool. If you have used instance-based learning algorithm instead, you would have found that Slovenia has the closest GDP per capita to that of a Cyprus, 20K. Okay, and since the OECD data tells us that Slovenia's life satisfaction is 5.7, you would have predicted a life satisfaction of 5.7 for Cyprus. If you zoom out a bit and look at the two next closest countries, you will find Portugal and satisfaction of 5.1 and 6.5 respectively. 1 second, I'll be right back. Okay, so here we go. If you zoom out a bit and look at two next closest countries, you will find Portugal and Spain with a life satisfaction of 5.1 and 6.5 respectively, averaging these three, which is pretty close to your model-based prediction. This simple algorithm is called k-nearest neighbors regression. In this example, oh man, I remember this shit. K equals 3 in this example, right? Here you can see it here. Replacing the linear regression model with k-nearest neighbors regression in the previous code is as simple as replacing these two lines of code. Cool. Yes. Yeah, there you go. We wrote this, and this is a form of supervised learning algorithms. Linear regression is labeled here, and k-nearest neighbor is labeled here. Remember that, boys? And logistic regression is a little bit different too. Anyways, so in summary, let's continue. If all went well, your model will make good predictions. If not, you may need to use more attributes, employment rate, health, air pollution, get more or better equality training, or perhaps select a more powerful model, polynomial regression model. In summary, we studied the data, selected a model, we trained it on the training data, i.e. the learning algorithm searched for the model parameter value that minimizes a cost function. Finally, you applied the model to make predictions on new cases. This is called inference, hoping that this model will generalize well. This is what typical machine learning looks like. In chapter 2, you will explore blah, blah. We have covered a lot of ground so far, so about useful, most common. So we can go wrong. Okay, that is the end of this section, and I want to go through it again, but I'll go through it trying to break it down and make sure that I understand every single part of it that I need to understand for this. So we have instance-based here and model-based. So instance-based is generally, so this one says here that, so this is called instance-based learning. The system, for example, the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. So this type of learning is done by the system learning. This type of learning is done by the system learning examples by heart and generalizes to new cases by comparing them to the learned examples. For example, oh man, how can I make an example for myself here? How do I put this in my own words? So for example, let's say we had, let's see. Oh yeah, okay. Let me think here. So we have, let's say we have a series of food items. Let's say we have a series of food items here. Right, we have a bunch of sandwiches. We have ham sandwich, egg sandwich, blah 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 sandwiches, and then we have a bunch of fruit, and we have a bunch of biscuits and things. And let's say we plot these on a graph, and generally all the sandwiches are going to be together, and generally all the biscuits are going to be together, and generally all the fruit are going to be together. And now let's say our new instance is, so we know what sandwiches and fruit and all these classes look like. Those are considered different types of classes. We have biscuits, we have sandwiches. Those are two different types of classes. Let's say we add a McDonald's burger to our instance as a new instance we're testing here. So we add a new instance that hasn't been seen before, and it's a McDonald's burger. It's a burger. We don't have any classification of a burger in our thing, but it's put amongst our little system, and it says that, well, the burger is closest to the sandwiches, so we're going to classify this as a sandwich. So that's how I'm understanding that. So for example, let's say we had a bunch of food items such as sandwiches and fruit. Here we have two classes, sandwich and fruit. Let's say we have the let's say we have a new instance, McDonald's burger. This is tested against two classes and is shown to be closest to the sandwich class, and therefore it generalizes. There's the word again, generalizes to be a sandwich. That's just for me to understand in the future. When I'm reading through this, I like to have goofy R examples as well. It's basically putting the instance against an average case base, and then if it aligns with that case, then it will be treated the same. Yes, cool. Yeah, that's how I'm understanding it as well. Hopefully. Okay, I think I understand that. For example, okay, so here's another example. We could run a clustering algorithm that, let's say we have a clustering algorithm that, we have a clustering algorithm that groups different types of animals together. Oh, there's an example here actually of animal grouping. So, where is it? Here it is. This is the TSNE visualization highlighting semantic clusters. Let's see what that is. So notice how the animals are rather well separated from vehicles, how horses are close to deer but far away from birds, and so on. Figure reproduced with, okay, whatever. So you see how like these things, so these are trucks and automobiles over here. So let's say we have a new instance and it's like a Subaru, race car or whatever. Well, we can assume that this race car will be plotted close to an automobile somewhere around here or something like that, and very far away from deer, so it would be classified under an automobile or whatever. That's how I'm understanding. Whereas, let me see if I understand model based. So let's see, we have a model based. It would most likely align there, right? So model based is different in that we first define a method. So we first actually visualize the data and we assume a model that we can like use. So that could be a linear model so based on what we observe the data is doing. So for this example, I guess, I don't know how I could, for this one here, it says here, oh man, another way to generalize from a set of examples is to build a model of these examples. Then use that model to make predictions. This is called a model-based learning. Okay, so I need to go over this again. So this one, I don't understand this. So this one, what is this? I don't understand this. I don't understand this graph and how it's doing it. Because this one just reminds me of the previous one where it's closest to the triangles or whatever. It's within the boundaries. Okay, so instead of individually, so the other one is closest, right? Instance based is like detecting how many closest near it. If it's like 2, then it's going to be considered a triangle. If it's 1 square, but here, regardless if 2 squares are close to this one and there's only 1 triangle close to this one, if it's within the line, then it's going to be considered that triangle or whatever. So in this case, it would pick up the square, which is 1, 2, right? Yeah, because there's only 1 triangle close to it, so it'd be considered a square, but that's not correct in the model base. In the model base, it would actually be a triangle because this is the model we've defined as these group of things here and these groups of things here. I guess. I don't know. I'm figuring it out. We'll figure it out. I need to make sure I get this drilled in my head. So here we visualize the data. We've got this information here and we visualize it, and we can assume that our model is a linear regression occurring, and we can create the parameters for the theta 0 and theta 1 by applying a, what was it again? You can either define a utility function that measures how good your model is, or you can define a cost function. So we apply a cost function. You can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's prediction, so the actual line itself, as against the data points in the training examples. So the objective is to minimize that distance. So we just find the best line that fits all. So best fit. If an email is like an X amount of words in the others is more rule based. If an email has like X amount of words in it, anything with the X range is out. Within the X range is out. Okay, I understood. The other is more based on if an email says something like, something like or link, you could rule it out based on the rule alone. Right. Okay, I think I understand it. That means that is more aligned with traditional. That sounds like it's more aligned with traditional programming, where the user comes up with a rule set, and based on those rule set, you exclude things. Or if you have something like that, I don't know. Like on Twitch, a lot of the Twitch scams have .com in it, right? They scam people with links, but they also have .org or no, not .org, but yeah, I know, like fucking 10,000 words essays. Yeah, true. That is true. Near neighbor would be like K nearest neighbor would be like if it's within 10k words, delete. See ya. It'll be like that. Actually, I'm wrong. Are you? God, okay, don't confuse me. Okay, hold up. Both do the same. The more I think about it. Okay, then we need to define these. This is the one that. The other one is just more accurate. Okay. And it also depends on the type of information we have, I reckon, or the type of data that we have, or data that we have. Okay, I need to read through this, okay? Again. So before you can use your model, you need to define the parameter theta1. So how do we define this? Well, how can you know which values will make your model fit best? Okay, so to answer this question, you need to specify a performance measure. So in the form of linear, we're probably going to use a cost function that measures the distance between the linear model's predictions, so the predictions on the line, against the actual bullet points of the training. Right, so that's what we're trying to, okay. And so this is where the linear regression algorithm comes in. So we have a linear regression algorithm that you can do you feed it your training examples. So we feed it the training examples. We feed the training examples to it, and then it automatically finds the parameters that make the linear model fit best to your data. So this is called training the model. So yeah, okay, understood. In our case, the nearest neighbor is like a larger generalization. Okay. In our case, the algorithm finds that the optimal parameter is theta. Okay, understood. That's the optimal, and we found that through a linear regression algorithm. Okay, cool. So let's say. So now we're moving on to what is this? Model-based learning. So that's what we're doing here. So we're doing model-based learning here. And so how does this work? So let's see. Let me just be clear up here. So for example, suppose you want to know. So I'll do a general definition of it. So it is model-based learning is where from a set of examples or instances, i.e. the training set, we build a model, which is then model of these examples. Then we use that set model to predict the future instances, and that's cool. Okay, so from a set of examples or instances, because that's what you call that, instances, you build a model. You build a model, and then we use said model on new instances to make predictions. Kind of like a okay, so I'm gonna italics this and build a model. Boom. Okay, so that's how. Okay, I think I understood it. Dude, it's always this shit that gets me, man. It's like this the difference. So the instance base is more individually, where you throw something there, and amongst the raw information that we've got, it's like, oh, well, you're actually closer to those two guys, so we're gonna classify you as that, actually, on a real note. But model based, okay, I understood it. Model based is like, here, I'm going to throw a bunch of data on the plot, but before I'm going to throw my new instance, I'm actually going to create like a way to gain an average in rather than like just throwing you there and just seeing which one's the most closest. We're going to make sure that we're going to group these guys over here, or we're going to have this curved line that follows these data points, and it's not exactly on the training data, but it's going to like average out to fit as best as possible. And then we're going to throw you, and based off of that line that over there, then we make a prediction, and then based on that we go. We don't see like what's closest data points based on the training data. We actually just see what's, if you're closest on the line, depending on what you're on the line or the group of information there. Okay, I understand it. I think I understand it. What's the advantages of both? I don't know. I don't know if it's mentioned here because I don't remember. It's gone past my brain. Hold up. Let's see. Don't know. One is faster, meaning that the model one is slower. No, it's not. The model one is not slower. The other one is slower. I don't know. It doesn't mention here. I haven't read that. I don't even know. I don't know about the quickness. I wonder if it mentions. Why would the nearest neighbor be slower? Because it has to go through all the information. No, maybe not. Maybe the model. No, because the model one already has a model. So you just put it on there. You just put it on there. You don't need to worry about any other data points. You just put it on there. So, and then it would give you the number. Right? It doesn't have to check anything. It doesn't have to check all the data. It doesn't have to do anything like that. In my head, it feels like it would be quicker. Am I wrong? I don't know. I don't know. The nearest neighbor one, if there's like 2 or more guys, you have to be like, oh, okay, how many more guys around me? How many more guys around me? I don't know. I actually don't know. Okay, I have to find out then. Model-based is typically faster. I was correct! And more accurate than instance-based learning, but requires a large data set and expert knowledge of statistical and mathematical modeling. Okay, I don't know. Well, generalizes well to new situations, can capture complex relationships. What is this? Cons requires. What is the cons of instance-based learning? Cons requires significant computation and training time. May not perform well with noisy data. So, it's hard. Model-based is harder to build, but obviously it'll perform better. But also, the instance-based one, if you think about it, the instance-based one, for it to be really accurate, you have to have huge amounts of information, like a large amount. If you want it to be perfect, right? Like for example, here, this is like, let's say here, for example, we populate like 1 million like points here. Let's say, for example, this one, right, this one here. Okay, we have like a bunch of dense information, then we can assume that it can be quite accurate. But like in this case, there's really lots of gaps here, lots of like missing information. Like it might. That's why we kind of generalize this to a triangle. But in the case where of model-based, we can. It'll take some time. Obviously, you have to determine what type of what type of method you're going to use, like what type of model you're going to employ to group the said data. You also have to find the best like theta values or the numbers to kind of like to make the curves or whatever that you're using. You have to use the best kind of like, you have to use the best parameters to get the best possible, most accurate version of the predictions. And so the training and the preparation time is harder to build and takes time, right? That takes time to do. But the end result will yield some really fast results because you're generally just throwing it at the model and seeing what happens. You don't have to, it's not, am I getting that right? Okay, but also instance-based learning, by the way, it can capture complex relationships, efficient for so it's only efficient for large data sets, but it generalizes well to new situations and can capture complex relationships. The other one, let me see the other one. Model-based says the advantage of model, the ability to encode environment data. I don't even know what that means. While disadvantages include, what does that even? Model-based reinforcement learning. Okay, this is model-based reinforcement learning, bro. Model-based learning is typically faster and more accurate. What is this, bro? Give me this. Oh, fucking medium.com, bro. I'm out. I'm sick. Man. Okay. Okay, I'm gonna do it now. Okay, so model-based. If I prepare and put some time and effort into creating a model that works really well, that encapsulates all the data sufficiently, and then I create a new instance, and that instance is going to be quick because it doesn't need to test against the existing training data. There's a lot of data points when you're training the model, and that's what instant data uses. It holds a lot of information for you to compare with that new instance data. So that becomes a slower process, I feel like, than having an established curve or line that you have there. You plot that a single number and it will give you an answer and output. That's why I think it's quicker, if that's what we're understanding. Keyword you put there is established. So here, the model-based. Wait, what's bad about model learning? Wait, are you saying that the keyword is good or bad? Are you? What's bad about it? Establishing. You're assuming that it belongs in that group. If it's an established thing, you can easily. And it's harder to, and it's also harder to adapt to newer situations because you have to train, you have to go back, retrain a newer model that accounts for the changes. Okay. It is easily biased as we established based on training data, on prior training data. Meaning that changes in data would require remodeling, which could then alter the result. Yeah. So this is like a con here. So this is that. And then, however, it is quicker due to the established yeah, you're right. I get it. It's quicker due to the established nature because it needs to simply test against a curve or a line based on data rather than comparing directly to raw information. Think of it, so you can also think so a con could be you could also consider this as a time contingent method, as it is difficult to define. Sorry, it's difficult to incorporate new information without remodeling, right? Retraining or retraining rather. But also, as you said, 10 years ago, we may have used information or data to build a model. Use data to build a model. Now let's say we have. Now let's say we apply that model. Let's say we apply that model to current period. We are assuming that model still applies, of which it may not. Okay. Okay, but here we have instance base. Instance base. Yeah, picking shapes by eye versus sieving. Yeah, I guess, but I need to just think about it for a second. Plus, so plus is for this instance. Instance base is less biased, and can adapt to new data efficiently, right? Because you just add it and it will alter accordingly. However, but no, yeah. So you do that. It's less biased and can adapt to new data efficiently. So the cons is it requires large amounts of data. Tell me when you're done. Okay. It requires large amounts of data for it to be considered viable, enough to find meaningful relationships between data points. Okay, so instance-based learning provides various benefits. Flexibility, it can adapt quickly. It can adapt quickly. Changes, it does not rely on previous built model. Changes as it does not rely on previously built. It does not rely on prior model. Ease of implementation. The algorithm is ease of implementation. The algorithm is easy to implement and understand. No training phase. It does not require training phase, as such instance represents itself. Yes, that's right. Yeah, that's what yes, that's what's in my head. It's like basically how I'm imagining it is instance based is like you're just basically plotting a bunch of points, and over time you might collect new points or whatever, and you just plot it, right? You plot it, and then let's say you got a new one, and then it's a green dot, and then you put it on the thing, and then you just be like, oh, okay, cool. It's like really close to these guys, so I guess it's one of them. But then the other version is, so now I think I completely understood it. So now the other version, model based, is based like we throw in a bunch of data. Let's say it's encapsulated in time. Let's say today I decide to use a bunch of data today, and I put it and I build a model. Now I built a really good model that can predict the an instance and where it would be. So now that I've used that data and I built a model, and now it's quick because I don't have to look at and like compare everywhere. It's like automatically done, like with the model, based on the model. It's based on the data, so it assumes that it's correct. It assumes that it's a part of a certain class if it lands in that, based on the prior data, based on the prior information. But now, let's say it's been a few days and there's new data. Now, I plot it, and let's say we made it two models. We have the old one and the new one. And let's say the old one, if we plot it, it gives us that result. And then we plot it on the new model. Now it'll be different. It'll be classified as something else, or something. It might be classified as something else, because the prior model did not have as much information as we do on the next few days. and it's based on like previous information rather than current information. Whereas it's more difficult to implement newer information because we are like basically it's more difficult to build new information because we have to retrain the model. We have to retrain a new model based on current information if that is relevant. So we have to make sure, okay, so one is like building a sieve, which is hard to make, but the other is picking it out one by one. Sieving shit would be much faster. Exactly. So the reason, this is perfect. Sieve is such a good example. This is like building a sieve. Yeah, this is such a good analogy. Sieve. It's faster. This one here, this is like comparing with the eye, comparing data points with the eye against the training data. Cool. Okay. Sorted. Issues if suddenly the shit you wanted larger than the sieve, but you can still do it, but you can still do it by eye. Yeah. Okay, perfect. But the cons with this one is like if you don't have enough information, then it's not reliable enough. The instance based, you only have like, let's say you only have like 5 points, and you know what I mean? That's the bad part about instance based. It requires too much information, but I mean, so does the other one. You need information for you to build a model, but you can generally build a model based on it in the information and kind of guess how it is based on the averages, right? I don't know. Realistically, you need large amounts of information for both methods. Instance based is just less biased because it can react to new information quicker than model based. Whereas model based is similar, as you said, you're building a sieve for that particular time period and for that particular period in time. Whereas in a few days' time, that sieve becomes obsolete as new data comes and will be considered something else. Okay, I think I understand it. I understand it. For the most part, I understand it. I think I got it. I think I do got it. Thanks for that. Appreciate it. That helps me a lot. Because this is probably one of the things that I stumbled upon quite a bit when I was reading it the first time. So I appreciate that. Yes, understood. Good. Thank you. I think I get it. I got it. I think I get it, and I got it. Thank you. See, you are a good teacher. Are you becoming a teacher? Did you say that you're doing it? I don't remember. I got it. Okay. What time is it? How long have we been spending on this? 1 hour, 1.5 hours? Okay, I'm gonna stop. This took a lot longer than I thought, and I think I've absorbed a lot. I'm gonna play some games now, okay? We're gonna play some games. I might do some studying before I go to bed as well. So, I will come back to this. I'm gonna come back to this later on and just mentally test myself to make sure that I understand it. But I'm glad I nailed this part because this is probably one of the, especially during university, is probably the harder. We didn't really touch upon this information that much. We really only focused on things like actually doing the practical stuff. So I'm happy that I'm sitting down and making sure that I get all the basic concepts, because I think during that period of time, I really didn't understand the basics as well as I should have. And here I am now relearning it and having a goofy odd time sometimes figuring out what the fuck I'm doing. But anyways, all good. Okay, guys, I will be doing more of it again, okay? I'll be doing it again. You're probably going to use multiple types of machine learning. It's good to know what and when. Exactly. I agree. I mean, I had a rough idea of what to use, what, when, where. I am just, as I said, I'm just building a habit of going back and making sure I understand in the form of reading, and I'm reading more. As I said, I'm reading, and I'm deciding to read more and read related to my field. So hopefully when I finish this book, I'm moving. There's another book that I'm gonna read, which is this one here, and it's related to it's related to deep learning. So this is what we're gonna do. It's just the basics of the deep learning, and we're gonna learn about deep learning after this. We are tackling first this book here, and then we move to deep learning, because that's kind of like the next step, is to go through deep learning and understand deep learning. So hopefully I will, you know, hopefully I will understand, because this is probably the neural network stuff is really fascinating to me. So we're gonna do that. Okay, we're gonna do that. We'll get to that eventually, but we have to keep building this habit. I'm taking notes currently, and then and these notes are gonna be more dictionary, kind of like, for my own sake, in my own time I will make it a more like dictionary type of vibe for myself, and this should help me recall the information extremely well, like hopefully in my head. Where did you learn Obsidian from anyways? I didn't learn it. I literally don't know anything about it. I just kind of like started using it as a note taker. That's literally it, because it's got dark mode, and it looks cool when you build all the webs and stuff. Right now, I have 1 page, and this is just for this book. I've just got a giant page for this book. After I finish the book, I'm going to go back in my notes and break down everything into their own little dictionary vibe. So like, for example, polynomial regression will be in its own little section, and then it will have its own tag, and then it will be related to other books and things that I read. But right now it's just the beginning. It'll take a long time for me to complete this. It's not like it's just there for note taking. And if I want to go back, I can go back and, you know, just read it if I need to. I didn't learn it. I just found that I was like looking for note taking apps or whatever, and I just found on like people are using this more often to do that. So I was like, okay, fine, I'll try it. Why not? Good to learn Flash if you're bothered. It's I don't really want to do flashcards. I think the thing is, I just want to be like, I don't know, I just want to be able to read something and absorb it. You know what I mean? I just want to read something and absorb it. Flashcards are good for Japanese, but not like I used to use them back then, but not anymore. But like, you know, like things like that, you know. Anyways, let's get our game on. So we're gonna play some card games, but not Yu-Gi-Oh. Ha 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 ha. Got him. Not Yu-Gi-Oh. We're playing Balatro. Poggers. This game is really fun and really addictive. Very dangerous. Try to stay away from it. So I'm currently on this, because I did the other one. So you go here, 1, 2. So I did red, blue. I think that's it. But I unlocked some new stuff. But yeah, so we're on yellow deck. I just want to get 1 win with all of the decks, and then we go from there. Ace, ace. Okay, I need to think hard about this. Ace, ace. I'm gonna get an ace, ace, king, queen. I want to save that, so I'll go boom, 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 boom. So I can try and like correct my hand a little bit. Oh, I think we lose. I think. Three of a kind. I think we go hard here. Straight. Nice. Need 100. I think we made it. I think we did it. Yep. Let's go. Okay. So you just have to win, right? Doesn't matter how. Nah, it doesn't really matter how. There's two pairs. So all flushes and straights. Do we just buy the? Ooh, actually, this one's goes pretty hard in the long run. So let's just buy money pretty easily. I mean, get money pretty easily. This one, I think we can go for this. Ooh, flushes and straight. 80 plus treasure if played hand with flush. Joker plus 4 treasure if hand is exactly 4 cards. I reckon we go for this for now and just keep this combo going. Also, last night I learned how to do. Well, I realized that ordering the cards are really important as well. Like ordering the Joker cards in particular order and ordering these cards in particular order actually changes the way, you know, everything occurs, which is pretty good. So hearts are all debuffed. Why the ones in the bottom? What do you mean the ones in the bottom? What do you mean by that? Oh, why does the order matter? Basically, like the cards will trigger from left to right. The cards will trigger from left to right. So basically the Joker cards, like for example, if you have like a card that says plus 10 multiply, right? It'll add plus 10 here. And then you have a card that also says multiply the multiplier number by 2. Like you have a card that says that, let's say for example. So you don't want to order it in a way where the multiplication happens before the addition, right? You want to make sure you add, and then multiply all of the added numbers by 2, rather than multiplying like the smaller number by 2 and then adding on top of that. You know what I'm saying? So you can order it in a way that maximizes the multiplication value of the multiplier number. There'll be situations where I'll show you when that happens, but generally that's what it is. Holy shit. We're gonna make so much money, boys. Are you ready? Should we just make a... I think we just make a random joker. What is that? I've never seen that one before. Yeah, so here you go. Times 4 multiplier every 6 hands played. Okay, what is it? 2 common jokers must have room. Uncommon. I think we can sell this by 2. Skip the blind. Added 2 jokers. So here's an example. So you put the multiplication. So wait, yeah. So you put the score. You put these plus. You see here, +3 multiplier, +3 multiplier for each joker card I have, right? So plus 15 right now, because I have 5, and then +3 for every club suit that is played, right? So these pluses will go from order. The cards will trigger from left to right when I play my hand. So it'll go bing, 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 bing. Then it will check all of these cards. So if I put this card at the end, it will multiply by 4 on the 6th hand. If I, you know, yeah. Okay. I got a straight. Oh! This card is broken. Where is it? Where is it, man? Where is the card that makes it? This card, all flushes and straights can be done with 4 cards is ridiculous. That's fucking stupid. Because then you just buff the straights and the flushes. The multipliers of those, and it goes crazy. So for example, this is a full house. How often do we have a full house? Quite often, right? I'm just thinking. +5 hand size, reduced by 1 every round. This is like scary. I don't know if I want to do this. +1 consumable slot. First I'm gonna buy this. Full house is buffed. Do we open 5s? We open stand. Playing cards, or do we buy this joker card? I think I'm going to keep. I think I'm gonna keep it. I think I'm gonna keep this. I'll probably go for this one here, so we can add more goofy consumable slots. Let's go. Next round, we got the boss. All spade cards are debuffed. That's okay. I don't really care that much about them anyways. Queen, Jack, 10, 9. That's a straight. Let's go. Oh, we can go 2, 4. Yeah, no, that's good. Might as well use the dead card while we can. 10, 10, 10, 10. 22 multiplier, so 1,500. I want to get it now, so we go 7, 7. Oh man, look at this discarding. I'm gonna skip the next 2, by the way. I'm skipping the next 2 rounds, because then this will apply a full multiplier. So I would rather apply that entire buff to my whole thing. So tarot card appeared 2 times too often. Enhances stone cards, 1 in 2 chance to... don't care about that very much. I'm gonna go with this one here. Enhance 2 to bonus cards, creates 2 random tarot cards. Why wouldn't I take that option here? And then we go temperance, jokers max. No, I don't care about this. Select 2 cards, can go to the left to the right. Okay, no, I'm good. Okay, we go next round. And then we skip this, and then we go and we skip initial cards and booster packs in the next shop are free. So let's go. We're gonna do that, and I'm gonna go crazy. Because now what happens is I can turn. Why skipping good? Because I'm just trying to time this multiplier, 1 remaining. So I think, does it apply now? 1 remaining. Let me just test this out. Hold on. Let's say it's 1 remaining. So cards played. Okay, let me just try this for now. Let me just try a pair. Oh no, but I don't want to try. I want to try something big so that I don't screw up. So what are the clubs? These are spades. Let me go this one and this one. If I want to use this. On this times these two into those. And I got 3, 3, and then we go 2, 3. Let me just try this. Hold on. Oh, it's active. Damn it. Okay, I need to. Okay, now I know it's active. Oh, it's active now. Oh, no, it's active now. Okay, good. 6, 7. I'm missing an 8. King, queen, jack, 10, 9. We got a straight. Ooh, and this is gonna go so crazy. Watch this number. Okay, I lose the money for every card I play, but I don't really care that much. Because all my cards are free next. So 19 plus multiply by 4, 76, 6,000 baby. Sheesh. That's why I skipped the next few rounds so that I could time this up. So I defeated the boss, which is good. This is 1 free reroll per round. Oh, dude, that goes crazy actually. Hold the phone, bro. Hold up. Let me do Celestial Pack here. Then this one goes 3 of a kind, straight. Yeah, straight will give me a lot of shit there. Good. Then we open another Celestial Pack for free. 4 of a kind, 2 pair, flush. 3 of a kind, full house. We go for flush. Flush will also give me a lot of juice. Boom, and then we go. Oh, we can go for another one. I think we go for full house, I reckon. And then the problem is I think you can sell this 2, 3. I think sell this one. Selling this one. Selling this one. Grabbing this. Buy and buy. Then reroll this. Grab. I don't think this is good. Don't think that's good. And then we can go to the next round. Or we could sell this one for 2. And then we can buy this one. But I think I'm going to go next round. And then this one is going to... we're gonna go do this. Gain 2 different new ones. So for a pair we get this and we get 1 free reroll. Nice. So we have 3, 3, 4, 5, 6, 7. 1, 2, 3. We need 1 more red card, so I'm going to go and get rid of these 3 cards. Okay, I regret that. Oh, yeah, sure, I got you. Right here. I might lose actually. Damn it. Getting pretty unlucky here. I think I fucked up with my choices in the Joker hand, I think. 8, 9. No, I'm missing a 10, man. I'm missing a 10. No, I did fuck up. I did fuck up. I fucked up. I shouldn't have gotten rid of the multiplier jokers. I think I should have kept them. Alright, next base edition shop joker is free and foil and holographic. Actually, I think if we do this one and skip the next one, bro. Sheesh. Doubles money. Hell yeah. I think that's pretty good. And then oh, yo! This Joker gains every time a playing card is added to your deck. Bro, this one goes hard. Oh, yo. Got him. Whoa. Holographic plus 10 multiplier. We're buying that, boys. Every straight, we can buy and use that one too. I want to re-roll the packs though. I want cards. I don't want. I need cards like right now. I need to re-roll this. Select two. Okay, let's check arcane pack. Let's see what happens here. Creates 2 tarot cards. Let's use this one. Damn it, we can make one of them into holographic. That doesn't work. Let's see this one. 3 cards to become hearts. 2 random planet cards. 3 of diamonds. Wait, what cards do I have mostly here? We haven't yet broken like multiple numbers on this. Have we? We have 13 red, 12 blue, so we're definitely not making blue, but I think I'm gonna lean towards hearts. I think we make more hearts here. How many blue do we have? We have 12, so just convert all blues to hearts. So 1, 2, 3, the high number cards, and make them hearts instead. So now we're leaning in towards the red. And do we care about pairs? Convert the other card to the right. Don't know if I reroll. Maybe I reroll here. Ooh, we got this, a common holographic. Yes, please, and it's 0 cost. 1 in 6 chance that this card is destroyed. All right, not a fan of that, but whatever, I guess. Yes, we buy a straight, 100%. So now a straight multiplier is gonna go so crazy right now, dude. This one says that gives $1 per hand. So I gain $3 if I skip this. No, I'm good. I'm gonna probably can gain more than $3 here. So we go 4, 5, 6, 8. Oh, we go king, queen. Nah, so we get rid of this. Oh, yo. Oh no, I fucked up. Go 1, 2, 3, 2 pairs maybe for now. Just do that. 32, 42, 15. Sheesh. That card got destroyed, no. It was 1 in 6 chance. That's lame-o. 2 common jokers go crazy, but we need to get a standard packs, bro. Standard packs. We gotta wake up our packs, brother. We got 7 of diamonds. We got a blue chip, blue seal. Creates a planet if for final played poker hand. Don't. Okay, sure, fine. Let's do this, and then we're gonna go next round. Oh, that one goes pretty crazy. Actually, that goes pretty crazy. 2 pairs. Yeah, 2 pairs. Or we can go. No, yeah, I think we go like this. 11. 11, 10, 10, 50, 10, 15. $7. Yo, let's go standard pack. Standard booster pack. This gains +2 multiplier for each reroll I do. Lame-o. Wait, all cards and packs in the shop are 25% off. Bro, I gotta buy this. I gotta sell this. I think we sell this too, maybe. But we'll see. None of these are good. I'm getting a stone, bro. Let's get this one. Glass card is pretty crazy, honestly. I think we sell. Oh, we can go crazy with the straight though. Yeah, we're going crazy with the straight. Holy, that's gonna be pretty crazy. I think I'm gonna sell this, maybe. Yeah, I'm selling this. And let's just try this. What do we get? It gives us +8 for every pair. 1, 2, 1, 2. If it contains a pair, it's pretty good already off the bat. 1, 2, 3, 4. +8, +10, +15. 1.75, 61. That's 3,700. Already passed, baby. Let's go. We are going to immediately get this one. Okay, we're going for diamond here. Yeah, we're going for diamonds here because I don't want to put more unnecessary ones. I'm selling this one. This one is for 50 chips for the pair. This one increases selected rank. We're gonna go spectral pack. And we're going to convert all cards in hand to a single random rank -1. This one, add a foil holographic or polychrome effect to one selected card. Add a negative to a random joker, -1 hand side. What does that mean? +1 joker slot. Ooh. Destroy 1 random card in your hand, and 3 random enhanced face cards. I'm going with the risk. Please be red. Oh, they're all aces rather. My bad. I forgot. I thought it's rank, not color. Idiot. Skipping this. Selecting this. What is that? Earn 5 for each discarded king. Cool. So we go 9, 8, 7, 5, 3. So we go. We should probably get rid of these. Discard. Jack, 10, 9, to queen, and 8. That's a straight level 4. We basically won on the spot, I think. 1, 2, 3, 4, 5, 6, 7. Sheesh. Oh, enticing, but no. Every spade we have, I think I'm gonna get rid of. Oh wait, what does this say? Ah, I'm good. I think we get rid of this. I think we get buy some standard packs, bro. Yes, I love hearts, so we're gonna make more hearts. Big number here, 2.25 multiplier. Should we re-roll? No, we're not gonna re-roll. We're going to. I think we can buy this for 0 and then just sell it. 3. We can go for an arcane pack. Why not? This one goes crazy if it lands. Yeah, please, please, please. Yes! Plus 50 chips. Shiny plus 50 chips, baby. Let's go. All face cards are drawn face down. All good. Adds the sell value of all other jokers to malt. Plus 12. Okay. So these are our faces. So 9, 7. So holding this. I think we just discard these. Got an ace. Double ace. So we got ace. Pair. I think. Let's go. Popping off, baby. Nice. $17K, baby. Let's go. Let's do all this. Oh, but this ace card kind of goes crazy. Nah, it doesn't. Actually, I'm gonna sell this. I'm gonna buy a mega standard pack here, so we can get some busted cards. Ooh, this one goes crazy actually. And also the red. I like the red. We're going crazy with the red. $4 for a tarot card. Yeah, sure, why not? Let's open it up. Select cards to become 3 of diamonds. 1 stone card. A wild card. Let's see. Let's make this a wild card. No, we're not gonna make that a wild card. We're gonna make the aces a wild card. No, we're not. We're gonna make the blue ones a wild card because they need to count as other suits. I mean, other ranks. Or other, sorry, other, yeah, suits. Other cards or whatever. Ooh. Should I skip this and then... Oh man, skip. We're going for it. I don't care. We're skipping. This is crazy. Double money. I get 50 gold at the end of this, boys. So club cards go crazy here. All face cards are debuffed, right? So that's fine. Wait, we got 4 of a kind. Let me discard these 2. Got 1 tarot card. 1 card becomes a glass card. I'm gonna give it to this. Use it on this card here, please. Here we go. Are you ready? 1, 2, 3, 4 of a kind. Club. $17K, 1 shot. Big. 3 aces and 2. That's a full house. So we might as well do that. 1, 2, 3. 1, 2. $34K, big. Oh my god, look at all the coin I'm getting. Holy, 58 payout. Playing cards can be purchased from shop. That is so big, actually. Holy shit. That is actually insane. That's actually, I think that won me the game on the spot right now. Reroll. 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 Yes. We add for $1. No. I'm gonna go jumbo pack. Two random tarot cards, wild card, creates a random joker. Sell this one for 2. Creates a random joker. This is just a random joker. What is that? Ooh, give plus 25 for each stone card. Oh shit, that actually goes crazy. Wait, I think that's pretty good actually. Let's check out this. I think we throw this away now. Because I think we got broken cards, so I don't think we need this anymore. I think we just go with this. And then we do another judgment to see what other joker we get. Oh. Yo! Oh, I think we just won. I think we just won. We just won. That's crazy. We got a 2.25 multiplier plus a 3 times 2. Dude. We literally do not lose. We don't lose. I think we got this. I think we got this. I think the rock one is probably changeable if we get another multiplier one. Gives a spectral pack, sure. Converts all into a random suit? No. Destroy 5 random cards in hand, gain 20. Honestly, I'll take the bet because we don't really have quality hands here. But then do we lose a multiplier? Do it. Yeah, no, we don't lose a multiplier. Let's go. Next base edition shop is polychromatic. Oh man, do we skip? Do we skip? We skip. Oh, I'm going crazy. Alright. We're going crazy. First hand is drawn face down. Oh good, I'm just gonna skip my whole hand here. We're gonna sort by rank. So we're gonna keep the high ranking cards and then I'm just gonna get rid of the low ranking cards. Everything from here to here. Discard, bye bye. So with that, 1, 2, 3. It's kind of lucky. We hit a pair at least. 250. We hit 30. We basically nearly got it with a weak hand too. So 10. I'm gonna discard this. Gonna see what tarot card. Oh, use. Yo. Okay, and then we're gonna go. 2, 4, 6. No, that's okay. We're gonna go. We're gonna discard. Maybe get rid of these ones. I think we get rid of these cards here. Discard. 1, 2, 3, 4, 5. Yeah, I think we go for that. 2 pairs. 11, 11, 10. Buff. Buff. $313. We just hit 129k. Brother, I'm pretty sure we popped off. We got 12 coins for that. Ooh! I think this is worth selling this now. Buy this. This one, we're gonna add some more playing cards to our deck. We're gonna add more hearts. More hearts. Planets, reroll. Doubles money, yes please. Yes. Oh no. It didn't even matter. I had a whole debuffed hand too. That's crazy. Permanently gain +1 hand per round. That's fucking stupid. That's so stupid. +5 hand size, reduce it every round. I'm gonna open this first. Yes. For flush we +10. I think we just add some cards again. Reroll. We just add some cards again. Dude, we're on 5 multiplier. Okay, let's do it. Dude, we popped off. We got the god run. Holy shit. It's game, boys. Holy. That was sick. That was sick. Alright. We completed that run. Spectral cards may appear in the shop. Start with a hex card. Add a polychrome to a random joker. Destroy all other jokers. +1 card slot available in shop. Damn. Buy a total of 50 planets. Alright, play. So we're not going to continue this one. We're going to go for new run. We're going to go for green deck. So this one says at the end of each round, $2 per remaining hand, plus $1 per remaining discard, earn 0 interest. Meaning that the better we play, the more money we get. So the beginning games are not going to be so easy. 1, 2, 3, 4, 2 pairs. Let's go. 1, 2. Done. Okay, good. So we get 4 coins here. No interest, but just 4 coins. I think this one is pretty good. This one is also pretty damn good. 25%. It'll be future proofing essentially here. Should we might as well try for another joker, like a decent joker. Let's have a look. 2+ for each card and deck. 100 chips for, I think this is good for 100 chips if played hand it contains 3. No, I think this one's good for now. Soul diamonds are debuffed. Pretty good. That's pretty good, and this is also pretty good. Let's get a standard. Got full house, baby. Nice. Ooh, we'll take it. Sell this card to disable the current boss blind. No boss is active. I don't really give a shit. 3 diamonds, 2 spectral cards, and we want to go for planets maybe here. We can go for both. We'll go for both. We'll do this first. And here we're gonna go for 3 of a kind, 2 of a kind. Let's do a pair together. Pair is pretty common. And then we're gonna go for this one, which is a spectral pack. Ooh, +1 Joker slot, but we get -1 hand size. Yeah, we'll do it. We gave it to the wrong. We gave it to the bad Joker, man. That's okay. We'll do this. We're barely making it, which is not good. We need to get more multiply. We need to get a multiplier card, like, badly. Each king gives 1.5. It's 2 point. This Joker gains every time a planet is used. That's pretty good. Playing cards in the shop. So this one's pretty damn good. And then we just have to go into a celestial pack. And then we just go use a planet card. We can just go full house. And this one gets a buff. Now we should be doing business. We can add one more, why not? We can add one more. Arcane pack. $14, $13. Two lucky cards, glass card, gold card, diamonds, clubs. So I think we just use these. This one. So we want two. No, we lost this one, I think. Oh, Billy. We lose. Yep. I think we lost. Damn it. That was cool, but damn. Damn, I fucked up. Sorry guys. Damn. Oh my goodness, that's crazy. Okay, this run is going a bit crazy. A bit sicko mode, to be honest. 3.4 multiplier. 1 out of 5 taros is going pretty good. I'm not gonna lie. Wow. Ooh. And that's when I sell this card. Shit, that's so broken actually. What the fuck? I think we just won, boys. I just got 400,000 points. What the fuck? Bro, that's broken. Holy shit. Oh, this is so good for me. Because we love planets. Planets is buffing our card here. Oh, creates up to 2 planet cards. Let me just go into a jumbo pack first. Let me go into a jumbo pack. And then I will just remove a series. I'm gonna remove this. I'm gonna remove these 2 cards. Use to remove it. See ya. And then I'm gonna create a steel card in the form of. One selected card as a steel card, so we can just hold this card in hand to buff it. And then we can go. Oh, these cards can all be hearts. Oh, maybe that wasn't the correct thing to do. Okay, and then these cards can. This one can make a planet. 2 pairs. So level 5 now. Full house is busted. 4.6. We can go for another tarot card. So look. Oh, if we land this, it's game up. What does this do? This is doubles and give a total sell value. What is this? One selected card becomes a wild card. I guess this one can be a wild card, and then oh, this one can be a wild card. Use. So now it's like scratch, so it can be anything. 2 cards can be molt cards. So no, that's not. Let's do this one. I wanted to see if I can get a Joker to be holographic. Nope. Okay, never mind. Straight. This is gonna go so crazy. This one is detrimental to my game plan, so I'm not using that one. Not a fan of the vampire one. Oh, yep. Oh, can I not? Oh man, maybe I should sell this one now. No, maybe I should sell none of these. Just go next round. Mega Arcane Pack. Let's go. Increased the rank of 2 select cards by 1. Houses bonus cards. I'll create this 2 new tarot cards. Select. So this one is a sell, 100%. This one is select the card to be a wild card. Oh, I shouldn't have done that. It should be one of the other ones. Right, my bad. This should have been the one. Doesn't matter. Let's try this. Yes. Yes, dude. All right, we're gonna go again. All right, let's see. We can destroy some cards. We can select 2, so one becomes a wild card. This one becomes a wild card. There you go. So now these are all actually red, which is good. A steel card. Select 2 cards to destroy 2 lucky cards. So lucky cards can be these 2. Oh no, not these 2. These ones. Wait, does he keep the stamp if he's lucky? Let's have a look. We'll find out. Yeah, he does. Damn, this is gonna go crazy. If I run into that card, we're going crazy. All debuffed until all cards debuffed until 1 Joker sold. Sure, buddy. I got you, bro. There you go. I didn't even care about that card anyways. Just casual 200k. A highest score is 469,000 chips. That's crazy. That's pretty ridiculous, to be honest. That is pretty crazy. So we get +1 Joker slot and -1 every round. So this is going to be a hard deck to play. Yeah, that's going to be pretty hard. Let's see. We're going to have a pretty crazy Joker lineup, to be honest. +3 hand size next round. This is pretty rough. We can go 4 and 5 maybe. Okay, that is insane. I'm selling this one for that. That's literally the best card we could have got. I think we just win now. I'm pretty sure it's just game there. I think we can even sell this one, open a pack. We can't open up any packs though. No. No, dude. Ah, that was such a good combo. Damn it. It is what it is. Far out. +1 Joker slot, -1 hand every round. It didn't seem like that was happening, but I don't know. Maybe there's like a minimum. There's probably like a minimum. Oh well. Anyways, I'm gonna go to bed. Have a wonderful evening. Thank you for coming. I appreciate you all. Bye bye.